All right, welcome back to the deep dive. There's this very specific sound, a really visceral sound, that I think pretty much every computer user dreads.
I think I know where you're going with this.
It's not the fan spinning up, and it's definitely not the beep of a motherboard posting. It's that rhythmic, mechanical click, click, click.
The click of death.
Exactly, the click
Yeah.
of death. It's the sound of a hard drive just failing to find what it's looking for. And well, usually it's the sound of you realizing you haven't backed up in, 6 months?
It is the universal nightmare of the digital age.
It really is.
And honestly, it's a nightmare that is.
Yeah.
It's entirely preventable, or at least you can manage it. And that's why today we're looking at a stack of research on RAID.
Right.
And we're not just going to, define the acronyms. We're going to look at the architecture of survival.
The architecture of survival, I like that. So we're talking RAID.
Redundant array of independent disks.
Or, and I love this detail from the really old papers in our source material, inexpensive disks.
Which is actually a really important distinction to start with.
Yeah.
The original idea, the whole philosophy, wasn't about building one super expensive, invincible drive. It was about taking a bunch of cheap, fallible, consumer-grade hardware.
Things that were literally inexpensive.
Exactly. And using logic to make them act like a fortress.
Right. And that really gets to the core mission of this deep dive, which is storage virtualization. Because, when I open my File Explorer and I see Drive D, that's a lie, isn't it?
It's a useful illusion. Virtualization is the key word. You might see one volume, but behind the curtain, you could have 4, maybe 8, maybe 20 physical drives all spinning together.
And RAID is the conductor of that orchestra.
It is. And generally, when you build an array, you're chasing 3 things. Redundancy, speed, and capacity.
The classic pick-two triangle. You want it fast, safe, and big.
Good luck. You almost always have to compromise somewhere.
Okay, but before we get into the levels, the zeros, the ones, the fives, we need to talk about the brain of the operation. Hardware versus software RAID. This came up a lot.
Oh, yeah. And this is a debate that has shifted massively in the last decade.
It really has. The old school thinking was always buy a dedicated RAID card.
Right.
You'd plug this physical card into your motherboard, it has its own little processor, and it handles all the traffic.
And historically, that was the correct advice. CPUs back then were slow.
Yeah.
You did not want your main processor bogged down calculating storage math while you were trying to, render a video.
So you offloaded it. It was faster, but man, was it expensive.
It was. But if you look at the modern articles in our stack, the tone has totally changed. There's a lot of love for software RAID now.
So why the shift?
Well, for one, CPUs are incredibly powerful now. Your desktop processor can handle RAID calculations without even breaking a sweat. But there's a bigger reason.
Which is?
Proprietary lock-in.
Okay, explain that.
Let's say you buy a fancy hardware RAID card from manufacturer X.
Yeah.
You build your array. 2 years later, that card dies.
The drives are fine, but the brain is dead.
The brain is dead. And to read those drives, you often need that exact same card with the same firmware. If manufacturer X went out of business,
You're in a lot of trouble.
you are. The hardware itself becomes a single point of failure.
Whereas with software RAID, it's all managed by the operating system, or like you see with ZFS or BTRFs, the file system itself, it's hardware agnostic.
Exactly. You can pull those drives out of a fried server, plug them into a totally different computer, import the pool, and you are back in business.
That makes a ton of sense. And the sources mention ZFS a lot, kind of like this super RAID that does things hardware controllers can't, like bit rot detection.
Yeah, that's a whole deep dive for another day. But the short version is hardware RAID just knows if a drive is spinning. Software RAID like ZFS can actually check if the data inside the file has silently corrupted over time, and it can fix it.
Okay, that's impressive. So we know how it's controlled. Let's talk about how it works. The levels. And we have to start with the speed demon, RAID-0.
Oh, RAID-0, the hold my beer and watch this of storage.
I love that. So I'm looking at the diagrams, and the concept is striping.
Right. So imagine you have a large file, like a video file. In a normal system, you pour that data onto one drive, like water into a bucket.
And it takes as long as the hose allows.
Right. But with RAID-0, you have 2 buckets, 2 drives, and you split the stream.
So block 1 goes to drive A, block 2 goes to drive B, block 3 back to A.
You're writing to both drives at the same time.
So you're basically doubling your bandwidth.
Effectively, yes. 2 drives, you get nearly double the speed. 4 drives, nearly quadruple. It is incredibly fast.
And you get the full capacity. Two 1 terabyte drives gives you a 2 terabyte volume.
No wasted space.
But there is always a but.
There is zero redundancy, hence the name RAID-0.
The source graphics for this are just brutal. They show a 4-drive RAID-0, one drive gets a red X on it.
And the result is total data loss.
It's that bad.
It is. Because you chopped every single file into tiny pieces across all the drives. If one of them fails, you can't reassemble anything. You've lost it all.
So wait, if I have 4 drives in RAID-0, I'm actually quadrupling my risk of failure.
You are. You have 4 points of failure, and if any single one of them breaks, the whole thing dies.
Okay, so who on earth is this for? Why would anyone do this?
It's for temporary data, high-throughput stuff. Think about a video editor working on raw 8K footage. They need that massive speed to scrub through a timeline.
So they use it as a scratch disk.
Exactly. But they do not store the only copy of the movie on it.
God, I hope not.
If they do, they get fired.
Yeah.
You edit on RAID-0, you back up to something else.
Okay, that is way too stressful for my main system. I want the opposite of that. I want safety. I want to sleep at night.
Then you want RAID-1.
A mirror.
RAID-1's the warm blanket. It's mirroring.
Which is, I mean, it's exactly what it sounds like, right? I write a file, and the controller secretly just clones it to a second drive.
Instant bit-for-bit duplication. If you have 2 drives, they are identical twins.
So the trade-offs here. Redundancy is obviously excellent if drive A dies in a spectacular puff of smoke.
Drive B is just standing there holding all the data ready to go. And usually the system doesn't even stop. It just alerts you, hey, drive A is gone, but it keeps running off drive B.
It's seamless, but my wallet is going to hate this.
It is the most expensive way to get redundancy in terms of cost per gigabyte.
Yeah.
You are buying 2 drives to get the capacity of 1. You're throwing away 50% of your storage potential for insurance.
So what about performance? It's not as fast as striping, I assume?
It's interesting. Read speed is actually pretty good. Since the data is on both drives, the controller can read from both at once.
Oh.
A write speed, that can take a hit.
Because you have to write the data twice to both disks.
Exactly. And the write isn't complete until it's confirmed on both disks, so you're limited by the speed of your slower drive.
I saw an interesting note in the diagrams about something called disk duplexing.
Ah, yeah. That's for the ultra-paranoid.
Okay.
In a standard RAID-1, you have 2 drives, but they both plug into one controller. If that controller dies...
You still lose access to both drives.
Right. Disk duplexing uses 2 separate controllers, one for each drive. It's redundancy for the brain.
But for most people, the cost of RAID-1 is the real problem. I mean, if I need 100 terabytes of storage for my business, I don't want to buy 200 terabytes of drive.
It gets expensive fast.
Yeah, so we're kind of stuck. We have RAID-0, which is fast but dangerous.
Right.
RAID-1, which is safe but super wasteful. We need a middle ground.
We need the parity levels. This is where the math gets fun. This is how we cheat the system.
Okay, parity is one of those words that tech people just throw around. The source material calls it error correction info, but what does that actually mean? Give me a mental model.
Okay, let's do some very, very simple math. Imagine we have 3 drives. Drive A, Drive B, and Drive C.
Okay, 3 drives.
We're going to store data on A and B. Let's say I write the number 5 to Drive A, and I write the number 2 to Drive B.
Got it. 5 and 2.
Now on Drive C, the parity, I'm not going to store the data. I'm going to store the sum of the data. What's 5 plus 2?
7.
So Drive C holds the number 7. Now, here's the magic. Imagine Drive A explodes. The number 5 is just gone.
Okay, so I'm left with Drive B, which has a 2, and Drive C, which has a 7.
Exactly. And the controller looks at that and says, something plus 2 equals 7. Basic algebra.
The missing number has to be 5.
Boom. You just reconstructed the lost data without ever having a full copy of it. You use the mathematical relationship, the parity, to rebuild it on the fly.
That's incredibly clever. So instead of copying the whole encyclopedia, I just keep a little cheat sheet.
Cheat sheet that takes up way less space. That's the beauty of it. You get safety, but you aren't sacrificing half your drives.
So RAID-4 versus RAID-5, they both use this idea.
Right. RAID-4 was the older way. It dedicated one specific disk to be the parity drive.
I think I can see the problem there already.
Yep.
If I write to disk 1, I have to update the parity drive. If I write to disk 2, I have to update the parity drive.
Every single write hits that one drive. It becomes a massive bottleneck. It just grinds everything to a halt.
So RAID-5 is the solution to that.
RAID-5 uses distributed parity. Instead of putting all the answers on one disk, it just sprinkles them across all the disks in the array.
So everyone shares the load.
Which means faster writes, no single bottleneck. It's been the standard for enterprise storage for a very long time. You can lose any one drive, and the math on the remaining ones can rebuild it.
But, and this is a huge but that showed up in all the recent research, there's this growing idea that RAID-5 might actually be dead.
The RAID-5 is dead argument. It's very real.
And it comes down to the size of modern drives, right? Back in the day, a big drive was, what, 100 gigs?
And now we have 20 terabyte monsters. Think about the rebuild process. You have a RAID-5 array with these huge 20 TB drives. One fails. You pop in a new one. Now the system has to read every single sector of all the other massive drives to do that algebra and fill in the new one.
It's reading terabytes and terabytes of data.
Which takes time, a lot of time. We're talking days to rebuild a large array. And during those days, your remaining drives are under 100% load.
And if they were all bought at the same time, from the same batch?
The statistical likelihood of a second drive failing during that high-stress rebuild, it's uncomfortably high.
And if a second drive fails in RAID-5?
The math breaks. You've got two missing variables in the equation. You can't solve it. The data is gone.
Wow, that's the danger zone. So what's the answer? RAID-6.
We double down. Enter RAID-6, dual parity.
So it's the same idea as RAID-5, but you're doing the math twice.
Two independent sets of math for every piece of data.
Which means I can lose two drives at the same time and still be okay?
Yes. You can have a drive fail, you can start the rebuild, and halfway through that long process, another drive can fail, and you're still safe. The system can still solve the equation.
That seems like it should be mandatory for large drives today.
In my opinion, yes. If you are building a server with large capacity drives today, RAID-5 is a gamble you shouldn't take. RAID-6 should be the baseline.
Is there a performance hit for all that extra math?
There is a write penalty. Writing to RAID-6 is a bit slower than RAID-5 because of those extra calculations, but for most file servers, that peace of mind is absolutely worth it.
Okay, so we've got the speedsters, the mirrors, and the math wizards, but there's one more big one, the rich kid option, RAID-10.
RAID-1-0, or 1 plus 0.
It's a nested level, a stripe of mirrors.
This really tries to get the best of both worlds. Imagine you take two drives and you mirror them. That's a RAID-1 set.
Okay.
You take two more drives and mirror those. So now you have two safe mirrored pairs.
Two little lifeboats.
Right. And then you stripe your data across those two pairs. That's the RAID-0 part.
So you get the blazing speed of striping, but underneath it all, every piece of data has a clone.
Exactly. It's incredibly fast for both reading and writing because there's no complex parity math to calculate. But you also have very high redundancy.
But we're back to that cost problem from RAID-1.
We are. You're losing 50% of your raw space again. To get 20 terabytes of usable space, you need to buy 40 terabytes of drives.
But I guess if you're running a high-performance database with thousands of users, cost is secondary to it needs to work fast and never, ever break.
That's the use case. For high I/O, RAID-10 is king.
Okay, let's try to boil this all down. A decision matrix for anyone listening who is like staring at a shopping cart full of hard drives right now.
Let's do it.
If I'm a gamer or a video editor and I need absolute max speed for temporary files and I truly do not care if I lose them.
RAID-0, it's cheap, it's fast.
Yeah.
Just don't put your family photos on it, please.
Okay. What if I'm setting up a drive for my operating system or a small business server where uptime is everything?
RAID-1 or RAID-10 if you have the budget and need more capacity. It's simple and it's robust.
And if I'm a data hoarder, I have a massive media server, I want tons of space, but I have to be able to survive a drive failure.
RAID-6. I really hesitate to even recommend RAID-5 anymore for new builds with large drives. Go with RAID-6. That extra safety is well worth the cost of one extra drive.
Now, before we wrap up, there's one final crucial point we have to make, and this is the one that really burns people.
Oh, I know exactly where you're going.
I have a RAID-6 array. I can survive 2 drive failures. I am invincible. I don't need a backup.
Wrong. Wrong. So dangerously wrong.
Why? I mean, if my data is redundant, isn't that a backup?
No, everybody repeat after me. RAID is not a backup.
Explain the difference.
RAID protects you from hardware failure. A motor burning out, a disk platter shattering. It does not protect you from logic failure or, more importantly, human error.
Give me a scenario.
Okay, ransomware. A virus gets on your system and starts encrypting all your files.
What does a RAID controller do?
The RAID controller says, oh, excellent, you're updating these files, let me help. And it instantly, efficiently, and redundantly writes that encrypted garbage to all of your drives simultaneously.
Ouch. So the redundancy actually works against you there?
It perfectly ensures the corruption is copied everywhere. Or, you accidentally delete a critical folder. The RAID controller mirrors that deletion instantly. It's just gone.
So RAID is about availability. keeping things online. Backup is about recovery, getting things back.
That's the perfect distinction. RAID keeps the server running if a part breaks. A backup, an offline copy in the cloud, on a drive sitting on a shelf, that is the only thing that saves you from fire, theft, viruses, or your own stupidity.
That is a very sobering but very necessary reality check.
If you take nothing else away from this deep dive, please let it be that. Build your RAID, enjoy the speed and safety, but have a separate backup.
And maybe think about that rebuild time. It's funny, isn't it? As technology gets better, as drives get bigger, some of these older technologies like RAID-5 actually become more risky.
It's a total paradox. We're reaching a point where the sheer volume of data is starting to outpace our ability to manage it with these traditional tools. It's why things like ZFS and cloud object storage are taking over. The old math is starting to crack under the weight of a 20-terabyte drive.
Something to think about the next time you hear that click, click, click.
Don't ignore the click.
Thanks for listening to The Deep Dive. Go check your backups, and we'll see you next time.